Ammonia is commonly used as a household cleaner, oftentimes being mixed with water, and or water would be used afterwards to rinse the area clean. So first we'd like to find out the molecular geometry of the molecule. Using this molecular geometry, we can figure out whether it's polar or non-polar depending on whether the dipoles all cancel out, and that would be dependent on the symmetry. And then we would like to answer the question of why water rinses it out so well. And so first let's start with its molecular geometry, and this is dependent on its Lewis structure. And so we begin by counting its valence electrons, 5 from the nitrogen and 3 from the hydrogen. So you have 8 valence electrons. Nitrogen can make the most bonds here. And so we'd have the 3 hydrogen bonds. We have no more valence electrons to put around them. But nitrogen's octet is still not full. It needs 2 electrons. We're missing 2 valence electrons, so it makes the most sense to put them on nitrogen. And so our structure would look like that. And so in order to now determine its molecular geometry based on this Lewis structure, we need to think about its steric number, or how many axial groups it has attached. So this is the number of bonding pairs plus the number of lone pairs. And so bonding pairs, we have 3 bonding pairs, and we have 1 lone pair on the nitrogen, so it has 4. And so for a steric number of 4, that would be sp3. Why is because s has a power of 1, p has 3. And so to fit in 8 electrons, you'd need 4 orbitals, and 4 provided this way. So this kind of just counts how many orbitals you need. And so it's going to be sp3 hybridized. So next up, we're just going to pull up a Vesper chart. We see its steric number is 4, but it does have 1 lone pair. And so what that means is that its electron geometry will be tetrahedral, but its molecular geometry is going to account for the fact that 1 of those axial groups is a lone pair, and so it's going to be trigonal pyramid. So if we just draw that all out right now, we will have N, 1 hydrogen slightly behind, 1 hydrogen slightly in front, 1 in plane. And then we're going to have the 2 lone pairs in plane but above, because that's the best place to put it. That way it can push these 2 bonds to make them over the optimized angle of 109.5, making these bonds less than the angle of 109.5. And simply because lone pairs repel more than electrons in bonding pairs, so it's going to cause a bit of a bigger push. So the forces won't be all symmetrical, making all of the angles the same. And so next, the question is asking whether it's polar or nonpolar. And so the way that we determine that is we will draw out the direction of the dipoles depending on the electronegativities of the atoms. And so hydrogen is less electronegative than nitrogen, and so its dipole would face that way. Again, same thing here, because you have the same 2 atoms. Again, same thing there. And then lastly, lone pairs are always the more electronegative one, and so this would point this way. And so what's going to happen is the angular components of this would all cancel each other out simply because of the trigonal pyramidal shape, and it would just leave a dipole facing up because of the lone pair, and another dipole also facing up because of the difference in electronegativity between these 2. Of course, this would not lead to them canceling out, and we would have a non-zero dipole moment left over, and that would mean that the molecule is going to be polar. Okay, next up, they'd like us to answer why water can dissolve ammonia. And so this is based off of the like dissolves like. So this means that polar solvents will dissolve polar solutes. Furthermore, both NH3 and H2O are not only polar, but have hydrogen bonding. And so due to how alike they are, water would act as a solvent, dissolving the ammonia solute. And those are your final answers.